So in the last video, we have explained the working of an asymmetrical square wave generation or the astable multivibrator to generate a waveform of different duty cycle. Now we have to discuss on the design, how to design this. Okay, so we already know that this the time period T1 and T2 here. The T1 is the on time and T2 is the off time. If we are considering this as a logic, then high value is an on state and low value is an off state. So the time period of this on state and off state depends upon the timer circuit, that is the timing circuit, that is RC network here. So this R and C, the current flowing path R and C determines this time period. So we know that when the op amp is plus V out, when the op amp output is in positive saturation or output is plus Vsat, then the diode D1 and resistor R3 conducts. Okay, if you don't understand how this diode D1 and R3 conducts, so please go back to the last video and see how it works. Okay, I have explained the working there. So at the time T1 or when the output is plus Vsat, then diode D1 becomes forward biased and the current flow will be from V out to D1, then R3 it is moving through capacitor C. So naturally this time depends upon this resistor R3 and the capacitance C. Okay, so the charging time depends on R3 plus RD into C. Similarly, this is the discharging time, that is T2. In the time T2, that is when the output is minus Vsat. When the output is minus Vsat, then diode D2 conducts, isn't it? So at that time, the charging time depends on R4 and C. So we have to take care of this and we have to design separately for these two time periods. I will show you the equation. So we know that the capacitor voltage across the capacitor as a function of time is equal to final value plus initial minus final into e raised to minus TRC. When I am taking from minus Vsat to plus Vsat, then Vc is equal to beta Vsat is equal to initial value is minus beta Vsat and final value it is recharging to plus Vsat. It can charge to plus Vsat into 1 minus e raised to minus TRC. These equations and derivations were there in Astable part 2. And finally, solving this, we will get T1 is equal to, we will get the equation here as T is equal to 2RC ln 1 plus beta divided by 1 minus beta. That equation you will get. So now what I am going to do is, in this case, when the output is plus Vsat, then this diode D1 conducts through the resistor R3 and the capacitor charges. So at that time, at time T1, or at time T1, then what is our this time T1 when the capacitor is charging or the output is positive? We know that the time T1 the charging path is R3 and D1. Okay, R3 and capacitor C. So I can write T is equal to R3 plus RD, that is the total resistance here. R is equal to R3 plus RD into C ln 1 plus beta minus 1 minus beta. Similarly, when the output is negative, we know that time period is T2, isn't it? So T2 is equal to the conducting path is R4 and D2. So the total feedback resistance become R4 plus RD. Okay, so T2 is equal to R4 plus RD into C into ln 1 plus beta divided by 1 minus beta. Okay, so now we have two charging times, that is charging time T1 and T2. T1 equation I have written and T2 equation I have written. Our main purpose is to design. We know that the frequency will be always constant, that I will tell you. Okay, the frequency will be constant, but we can design for different duty cycle, that is the on time can be 20 millisecond and off time can be 80 milliseconds. So the total is 100 millisecond. Okay, like that we can design for different time period. Okay, So we have separately written the equation for T1 and T2, and now we know that the frequency remains constant but the duty cycle changes. How is the frequency remaining constant? The total time period, the total frequency is constant means the total time period should be constant. So what is the total time period? That is the charging time plus the discharging time, that is T1 charging time plus discharging time is T2. I have written the equation, that is T1 is R3 plus RD into C and T2 is R4 plus RD into C. See, T1 R3 plus RD into C ln 1 plus beta by 1 minus beta, and T2 is R4 plus RD into C ln 1 plus beta by 1 minus beta. So I am taking C into ln 1 plus beta divided by 1 minus beta as a constant, that is R3 plus R4 plus 2 RD. From this we understand that this resistance R3, R4 and RD will be always constant, C will be a constant, and beta we are taking it as a constant. As a result, what happens? The entire time period will remain constant, so that the frequency will also remain constant. Okay, in this particular case the frequency or the total time period will be constant but the duty cycle varies. What is the duty cycle? Duty cycle is the ratio of the on time to the total time period of the waveform. I repeat, duty cycle is the ratio of the on time to the total time period of the waveform. That is, here on time is T1, T1 divided by T. So T equation I have found out, T1 equation also we know. So in order to find out the duty cycle, we will get it as R3 plus RD divided by R3 plus R4 plus 2 RD. Okay, now for 60, if we are asked to find out 60% duty cycle, then this is equal to 0.6. 60%, then we should design, we can take, we know the resistance of a diode, even we can neglect it, then we can take it as R3 divided by R3 plus R4, and we can design, we can put certain value for R3 and design for R4. Okay, so this is how we design for a astable multivibrator with different duty cycle. We have to find out the duty cycle first. If we are asked to find out 20% duty cycle, then R3 plus RD divided by R3 plus R4 plus 2 RD, that should be equal to 20% means 0.2. Then we have to choose R3 and RD accordingly. I hope you remember the design of this beta value. If beta value we are taking it as 0.46, then we can simplify it by using, we can ignore this ln 1 plus beta by 1 minus beta, so that we can assume the R1 value will be equal to 1.18 R2 value. Like that we can design and put, you can, if you find it very difficult to remember R1 and R2, just put beta value is equal to 0.46, so that beta, here beta is equal to R1 plus R2, here beta is equal to R1 divided by R1 plus R2. So, and that is equal to 0.46. Now you can design R1 and R2. And now what is the thing? Next we have to design this capacitance value. So we are taking duty cycle value and we are choosing what you choosing this value of R3 and R4. Before that, I should say one more thing, that there is a capacitance, that capacitance value you can take it as some standard value, that is 0.1, and you can design for first cycle, then change accordingly for R4 or RD. Okay, so next I am giving you a question, you have to solve this. So here just remove this 555 timer. Instead of this, you have to design an astable multivibrator for an output waveform of 60% duty cycle at 2 kilohertz frequency. Instead of instead of 555 timer, we are using it as our 741 IC. For that, you have to first draw the circuit, and what you have to do, you have to assign beta is equal to 0.46, and you have to find out the values for R1 and R2. Next, you have to the frequency it is given as 2 kilohertz. So 1 by 2 kilohertz, you will get the time period. That time period on time ratio, you will get the time period into 0.6, you will get the on time. That on time you have to design with this value. Beta you don't have to take it, R3 into C. So you select a value for C and you find out R3, then you have to find out R4 accordingly. Okay, I hope you understood. You have to solve this and submit in the Google Classroom. That's all for Astable multivibrator. Okay, thank you.